Before we get into some algebra tiles, I have a really important question for you. Why did the unicellular organism's friends unfollow it on Instagram? You know why? Because it was always taking selfies. Get it? Okay. So let's take a look at your pre-work. You should have taken a look at an algebra tile kit and drawn in the different types of tiles. And let's just make sure we understand what those tiles are. So one yellow represents 1, and the opposite of a yellow on the other side is a -1. And I want you to notice, just like with your integer chips, 1 and -1, they're going to turn into 0. There's 0 pair. Similarly, one green, a long green bar, is an x, representing some unknown value, and the opposite of an x is a -x. And x plus -x is 0. I also want you to notice something interesting about the x bar. Take one of just the single value chips, and notice that that perfectly aligns, because the x is a rectangle that's 1, but then it has a width of 1, but then we can't figure out exactly how many long it is. It looks like it's 5, and then there's some left over, and I suppose we could break them apart, but that's our way of representing that this is 1 times some number that we don't know, and 1 times some number is x. Okay, and then you should have also seen the blues. The blues are the squares, and the blue square represents x to the second power, or x squared. Makes sense, right? It's a big square. In fact, it makes even more sense when you consider that the relationship between the square and the green bar looks like this. And that's because the square has side lengths of x. So its area is x times x, or x squared. That's going to come into play when we start doing the distributive property. Just like the other chips, though, the opposite of x squared is -x squared, and together they make 0. Okay, so we're going to use these tiles for a bunch of different things. To start out with, though, we're going to build some expressions. And our goal is first to build it, and then it's going to be way too complicated. We're going to need to simplify them. All right, so the first one, x squared, means I'm going to take x squared plus x. I'm just building exactly what I see here. Plus another x. Let me zoom out a little. Plus 1. Plus another x squared. Plus x. See what I mean by way too complicated? Plus 1 more. Okay, so we have x squared plus x plus x plus 1 plus x squared plus x plus 1. Now you're probably already thinking that we could make this way simpler. Here's what we can do. We can first rearrange these tiles, and I get to do this with this expression because these are all addition. Remember, it doesn't matter if you add 2 plus 3 or 3 plus 2, you're going to get 5. That's the commutative property of addition. So I'll just rearrange this. I haven't changed what it means. It's still the same expression. So just to record what we did, this is x squared plus x squared plus x plus x plus 1 plus 1. So that's a little better because the things that are the same are next to each other, but it's still way too long. And we want to be more efficient, way more efficient when we're writing something. So we can make this simpler by noticing that this is x squared plus x squared, also known as 2x squared. I've got 2 squares. So I'm going to write that 2x squared. And remember that this means multiplication, so 2 times x squared. It's 2 copies of x squared. Okay, and now, I forgot an x right here. And now I've got 3 x's, which I can also write, if I put them all together into one little pile, I can write that as 3x. And lastly, this 1 plus 1, we can just write as 2. We just simplified this, combining like terms. Let's do another one. Okay, x squared plus 5x plus 3 plus 2x squared plus x plus 2. So now we've got a different situation where we've got these numbers in front of the variables. And just like in the last one, that number means multiplication, but we can also remember that what it's saying is I've got 5 x's. So let's do some building. So x squared plus 5x, so that's going to be 1, 2, 3, 4, 5, plus 3. 1, 2, 3, plus 2x squared. Okay, so here's 1x squared, here's a second x squared, plus x, okay, plus 2. All right, man, this is way too much stuff. It's way too complicated. We need to make this simpler. And to simplify it, we're going to combine the things that are the same, just like we did in the last example. This time, though, I'm going to circle those x squareds to show that those are the same. I'm going to combine them. And then I'm going to put a square around the x's to show that those are the same. And then I'm going to put a triangle around the 3 and the 2, because those are the same. We can combine all those things. All right, now let's do some rearranging. It's all addition, so I can do that. So I'm going to put the x squareds together. I'm going to put these x's together. And I'm going to put these singles together. Okay. And what I have left is 3x squared. 1, 2, 3, 4, 5, 6x. And 5. And at this point, you should be saying, hey, I noticed I could have done that. I could have said 1x squared plus 2x squared is 3x squared, 5x plus x is 6x, and 3 plus 2 is 5. Could have done it without the lab kit, which is great. You're already seeing the concept here. All right, let's do one more. And this one's going to get a little bit trickier, a little dicier, because it has my least favorite operation. Subtraction. I hate subtraction. It makes things confusing. It makes me much more likely to make a mistake. So whenever I have subtraction, to deal with this and to build it, I'm going to change subtraction into adding the opposite. Here's how I do it. Let's rewrite the whole expression, but instead of subtraction, like here, we're going to change it to adding the opposite. And let's keep going. Oh, got another subtraction. I'm going to change it to adding the opposite. And one more subtraction over here. I'm going to change it to adding the opposite. It's the same expression, just all that subtraction is now addition. And the beautiful thing about that is that that means that I can then rearrange this expression however I want. But let's not get ahead of ourselves. Let's build it first. Okay. 2x squared. So that's 2x squared. Let's see if I can zoom that out a little bit. So here's 2x squared plus negative 2x. Okay, so I've got 2 x's, but they're on the negative, so it's negative 2x, plus 3, 1, 2, and 3, plus negative x squared, plus x, plus negative 1. Okay, now just like I did in the last one, let's circle the like terms. So 2x squared, that's a like term. And negative x squared, I've got to make sure I'm keeping track of that sign. That's one like term. Now let's put a square around all the x terms. So negative 2x, being very careful that we are keeping track of that sign. X, that's another like term. And then one more triangles around those constants, those singles, keeping track of the sign, 3 and negative 1. Okay, so now when we've got these negatives and positives, just like when we were working with integers, we can rearrange them to get them to cancel out. So this negative x squared combines with an x squared to make 0. Oh, it's already getting simpler. This positive x combines with this negative x to make 0. And this negative 1 combines with this positive 1 to make 0. And look at, this is all that we have left. I'm going to write it. X squared plus negative x plus 2. Made that expression simpler. Okay, try this next expression on your own. Pause the video, and then when you are ready, you can unpause it and check it with my work. Pause it now. Alright, you should have first rewritten the expression with all of the subtraction as adding the opposite like this. And then what you built would look something like this. And then we can now find the 0 pairs. So there's 1 here. This positive and negative x cancel out. Same thing for that one. They make 0. And that's it. And so what we've got left is 5 negative x squareds, 1x, and positive 3. And that is the solution here. Negative 5x squared plus x plus 3.